Hello everybody. In this webinar, we would like to talk about an eye diagram as an important tool for signal integrity analysis. The typical instrument to do an eye diagram analysis is an oscilloscope. I have here in the studio Matthias as my colleague, and he will later on give you a demonstration on this instrument to show you the innovative feature of ROHDE and SCHWARZ. Hello Matthias. So here the outline of what are the topics that we have planned for today. I would like to start with some quick discussion about the high-speed interfaces. Then I would like to talk about what are the typical approaches for signal integrity debugging. And then I would like to dive deeper into the eye diagram discussion and talk about the eye diagram basics. And then in the next step, I would like to introduce you to the 5 typical steps of an eye diagram analysis. After this, Matthias, he will give a demonstration on the instrument itself, and then we want to conclude. So just on a very high level, if we talk about an electronic design that includes some high-speed digital interfaces, then we have typical challenges like the high-speed interfaces get faster and faster, and also the typical design, they get more dense. You have more components on one design. And this gives you a lot of challenges concerning signal integrity. So therefore, you should think about what is the right test strategy, what is the right tooling in order to acquire the right data. If we look here to an example of a typical design, we see on the left side an IC where we have some transmitting signal. I can take the laser pointer here. And this signal travels through the PCB board trays, through some connectors to a receiver part. We will see that there are some transmission losses. So at the output of the transmitter device, we have a signal with a wide open eye diagram. Then we will have some transmission loss over the PCB traces, and in the end, the eye even could be closed. So what are the typical reasons for such behavior? So first of all, there are channel-related effects like ringing, signal loss due to the traces, crosstalk from other signal traces, reflections due to impedance mismatches, but also there are effects from the transmitter side, like there could be an imbalance between rise and fall time. There could be some timing jitter already coming from the transmitter device. Or there also could be external sources. So you could have some EMI effects. There could be noise from the power supply or the power distribution network. Or there could be interferer from different functional cores. So with a digital signal, we see here in blue, we would like to transmit an idle 1 or 0. But because of all these signal integrity effects, we rather will have something like the red curve that is displayed here. So what are the typical tools in order to do some signal integrity evaluation? So first of all, I would like to mention the eye diagram. So I will give much more information about this in the following, but just as a quick start here, it's an overlay of a lot of bits from the signal sequence, and it really depends on how many bits you can overlay in order to get the right statistical information. Then the next tool would be the detailed jitter analysis. So with jitter analysis tools, you can look more into the individual components of the jitter. For example, you can look, is there more random jitter, is there more data-dependent jitter, and conclude on what you can improve on your design. And last but not least, there would be automated compliance tests. So for example, you have a USB interface, you want to certify this, that you are USB compliant, that the interoperability is given for your device, then you also could run an automated compliance test. But for today, I would like to focus just on the left side on the eye diagram. So let's talk a little bit about the basics of the eye diagram. So why is an eye diagram so important for signal integrity analysis? So first of all, it's a graphical tool that gives, with a quick glance, a lot of information already about the signal quality. So it is in superposition, like you can see here on the left side, of the individual bits within a data stream. You see, the individual bits are overlaid, and then the result on the right side, I get an eye diagram, and I see already with some different colors the persistence, where, let's say, there are more transitions, there are less transitions, and so on. Here on this next slide, there would be another view on how the individual bits are overlaid. So you see here the signal stream in yellow, and then the individual bits, they are overlaid one by each other. And with this, the eye diagram is filling and you get more and more information. Something very important in this context is that I need a reference clock. So this is illustrated in blue here. A reference clock gives me the timing of the slicing of the individual bits of the data stream, so that I have the accurate timing for the superposition of the individual bits. So this is very important. And that's why if we look to a typical serial high-speed interface link, we have on the left side the transmitter, on the right side we have the receiver part. So on the transmitter side we have a serializer. This is using then the bit clock. So for example, if we talk about a 5 gigabit signal, I need a respective fast clock signal in order to get my 5 gigabit signal serialized. Then this is transmitted via a signal tray, so it could be PCB, cable, connectors, and then it goes to the receiver part. And very important, on the receiver side, we have the clock data recovery, and this is giving the timing for the deserializer. The clock data recovery can use different algorithms like a PLL or a delay lock loop. For this, we don't want to look into further details there, just important, I need a clock data recovery if I have a serial interface. So if I finally have the overlaid bits in my eye diagram, I can get a lot of information out of this eye diagram. For example, if I look to the transitions on the left and on the right side, I see the jitter of my signal. If I look to the amplitude to the top level or to the bottom level, I see the noise of my signal. Then very important, of course, I want to transfer logical information ones and zeros. That's why for the receiver it's very important that I have an open eye. So that's why I look to the eye width and I look also to the eye height. So it's very important that for a good transmission I have an open eye. And I can combine this also that I put in the middle, you see this little gray area there, I can put also a mask inside in order to validate whether the eye is open over a certain runtime. Very important also, a lot of statistical information is included in the eye diagram because we have different jitter components, and especially the random jitter component are going to close the eye over a time. So that's why it's important that you have the possibility to collect the data very, very fast in order to get a high statistical confidence on your results. So what are the typical approaches in order to generate an eye diagram? The standard approach is, we see here in the middle, the components of an oscilloscope. On the left side, I have my device under test, and then I have my oscilloscope channel. And the standard approach is that I get the data into the oscilloscope. I have my AD converter, so for digitalization of the data. I have a trigger, typically an edge trigger, and then the data go to my memory. So I have a waveform acquired. And then I do the eye diagram generation in the post-processing based on the acquired data. So I apply, in order to get the timing information, I apply a clock data recovery algorithm. So it's a software-based clock data recovery. And once I have the timing there, I can do the bit-by-bit overlaying of the individual data bits. Because this is in the post-processing, of course, this takes some time. So we have here on the bottom of the slide some illustration. So I have a certain length of the acquisition. So for example, 100 microseconds. I do the acquisition here, and then I start the post-processing. And the post-processing takes time. And once this is done, I can do a new acquisition of a new burst of signals. And you see also with this illustration, for a long time, I'm very blind. So I don't look to the signal. So I have just the eye diagram information based on a few moments within the signal. So today we would like to introduce to you a new innovative approach in order to get an eye diagram and to get it in real time. So here the idea is to zoom with, or to scale with the oscilloscope to just a data bit and then use a clock data recovery in hardware. So if we look to the diagram here, again we have the input channel of the oscilloscope, we have the AD converter, and then we have a hardware clock data recovery as a trigger. So the clock data recovery, extracting the timing information from the signal, is the reference for the trigger. So this means I can overlay my individual bits just directly in the processing there. So I don't need to do a post-processing where I generate a software clock data recovery. So with the hardware clock data recovery, I immediately write the data with the right timing of the embedded clock to my memory, and then I can do the overlaying. And then as a result, you see here on the bottom of the slide, we have short glimpses to the signal, and they are continuously well distributed over the time. So we can continuously look to the signal. We get continuously information about the quality of the signal. And so we even can do a long-term monitoring of the signal with the eye diagram. We have a high likelihood that we can catch some interferer that do some distortion on the signal, that we can catch them with this approach. So we see a bigger advantage with having the real-time functionality. So how do we set this up? I would like to show this to you in the following. So we have a sequence of 3 or alternative 2 additional steps that I would like to present to you now. So first of all, I would like to start with connecting the signal to the device. And if we look to a high-speed interface, you can see that this is typically a differential signal. This means a plus and a minus signal is used in order to broadcast or to transmit the signal. The advantage of differential signal is that it is immune against disturbance from the outside, because interferers, they have the same effect on both lines, and because I just look to the difference, I cancel this out. So typically in test setups, I connect my oscilloscope to a device with 2 channels. So I have a board where I have, for example, 2 SMA connectors where I can do the test connection. So my differential signals is acquired with 2 individual channels of an oscilloscope. And this, of course, can be a big challenge, because I want to look to a differential signal. I want to trigger on a differential signal. And I also want to look, maybe later on, I want to do some compensation with de-embedding. So I want to apply an S4P file for correction. And so having just 2 single-ended signals for analysis would be a problem. So therefore, ROHDE and SCHWARZ R&D came up with some smart idea. They were able to implement a differential math block in the real-time path. So we have directly after the AD converter, before the data are saved to the memory, we have a differential math block. And you can see this here on the slide. So there are, for 4 channels, 2 differential math blocks. If we look to the top block, we have 2 input channels, just freely selectable, channel 1, 2, 3, 4. And then, of course, I get also 2 outputs. So I can select between, let's say, differential signal, common mode signal, also as a very important information of a differential signal. Or I also could switch back, of course, to just the standard P or the N signal. So the beauty of this is also I have a differential signal now in the real-time path, and I can use this also later on. You will see this as an input for my trigger system. So I can do with this approach here, with having a real-time math block, I can do triggering on the differential signal, and I can do straight analysis on the differential signal. The second step would be then setting up the trigger. So first step was setting up the differential signal. The second step now is about the trigger. And as I mentioned before, it is very important that you have a good timing reference. And the best, of course, if you have an embedded clock, would be to have a clock data recovery. So again, here this picture, just as a reminder, on the receiver side, we have this clock data recovery that extracts the embedded clock signal and takes this then as a timing reference. And the traditional approach is to do this in the post-processing. So the new ROHDE and SCHWARZ approach is to use a clock data recovery in hardware as a trigger reference. So we have two options available. One option would be with a data rate up to 8 gigabit, and the second option allows a data rate up to 16 gigabit per second. So we have the capability within our oscilloscope to set up a clock data recovery up to 16 gigabit. So this, the steps that you do with the oscilloscope are shown here on the right side of the slide. You select within the trigger dialog the trigger type serial pattern. This is connected to a clock data recovery. So automatically you get a clock data recovery. And then it's very important that you set up the nominal bit rate. And if you have a certain standard that you use for testing, for example, you look to a USB signal, then you can see here under this tab serial standard, you can select already some predefined standards. So for example, for USB 3.2 generation 1, automatically 5 gigabit is applied. So again, the advantage is that I can trigger with this hardware CDR already on a differential signal, or even I could select as a trigger input the common mode signal. Another advantage is that I don't need to do the clock data recovery calculation in the post-processing. So I do this in real time. And so I'm much faster in general with my analysis on a differential signal. So after this, the second step, setting up the trigger, we come to the third step, which is already about the analysis tools. So if I have an eye diagram, I want to look for jitter, I want to look for noise, I want to look also for an open eye. And two important tools that you can apply here are the mask. You see this in the diagram here in the middle, the gray area, or on the left and the right side, the histogram. So with the histogram, you can look to the jitter. If you apply the histograms in the vertical, you can look to the noise. And with the mask test, I can look to an open eye and do the verification there. The challenge for the instrument and for the user is really how many waveforms can I acquire in a certain time? How many bits can I overlay in a certain time in order to have a statistical confidence? Because I mentioned this already, we have jitter, random noise that is growing over time, and I need a high number of acquisitions in order to have a high statistical confidence there. So the ROHDE and SCHWARZ result you can see here in this next slide. You see here an example of an acquisition with more than 1 million waveforms acquired in a very short time. And this is due to our hardware architecture of the instrument. So we use a lot of hardware components in order to do a fast acquisition, fast processing. And with this, we achieve a really high acquisition rate. And also the components are built, or the analysis components are built into hardware. So the histogram and the mask test is supported by a dedicated ASIC. And with this, we can do a very fast analysis. And you see here on the right side some performance indicator. So in this example, we were close to 400,000 bits per second acquired or analyzed. You see also in the setup, the differential math is done in hardware. You see the clock data recovery is set up in hardware. And with this, we can achieve this really fast acquisition and analysis of the eye diagram. So what are the key steps in order to do this analysis? And first of all, you need to define the masks. You see this in the middle here. We have some possibility to create a mask directly at the screen. So you just say, create a mask, and you tip to the area of interest. You can define dots there, and then this is combining to a mask. And immediately the mask evaluation is starting, of course, you can also load some predefined masks and so on. So you have a high flexibility. But again, the key element for our mask testing is that this is supported in our ASIC in order to make it very, very fast. And then the second analysis tool would be the histogram. So you see here, the histogram is applied in the vertical in order to analyze some noise, or it could be also applied to the timing edges in the horizontal. So I look then for jitter. And also, if I apply the histogram and if I apply some statistical values that I want to analyze there, this is also done in hardware, so it's very, very fast. So the advantage again is I collect data very fast. I can catch with this approach also some rare interferer. So if there's some EMI spike coming in, I can catch this because I'm very fast. And so I also can look to long-term behavior of my signal. So these were the three, let's say, crucial steps for doing an eye diagram: differential signal, clock data recovery, and the analysis tools. But I promised you 5 steps. So what are the additional 2 steps? Let's have a look here. So first of all, if we talk about an high-speed serial interface, we can see that this is using some coding. And you see here on the diagram some example. I see in the yellow trace in the background, this is the analog signal. And on top of this, I see some decoding, some 8-bit, 10-bit decoding here. You can maybe recognize some comma characters or some data bits. And so I could say, I could apply a serial pattern trigger in order to focus my eye diagram on a dedicated portion of the signal. So also with our oscilloscope, we have the possibility to apply a serial pattern trigger combined with the clock data recovery on a high-speed serial data stream and look for dedicated bit coding and then apply there the eye diagram analysis. So if you look here to the screenshots here, in the middle you see the diagram or the dialogue of the trigger setup. So I have the clock data recovery, I have the nominal bitrate defined, and then I can say what type of pattern do I have. So if we support different type of coding like 8B, 10B, or 128, 130B, and so on. And I also could define here then a certain sequence of data pattern, and only if this shows up in my data pattern, then I trigger. And an example of an eye diagram is shown here on the bottom side. So this is from a 10 gigabit USB signal where I trigger on a certain sequence, and then I get an overlay of the signal sequences and can do a very dedicated eye diagram analysis on this. So just as an additional capability for debugging, for looking for dedicated signal integrity faults, we have the possibility to use a serial pattern trigger. This was number 4. And number 5 is about de-embedding. So if I look to a signal setup, I have my transmitter, I have my test point, I have some cabling or some probe, and so on. I have maybe a test fixture. This means what I see on my oscilloscope is different than what the device or the receiver sees. So with adding additional signal path components in the test path, I add transmission loss. And with the method of de-embedding, I have the possibility to correct such transmission loss effects. So typically, the transmission loss correction, the de-embedding, is done in the post-processing. Post-processing, I think I explained this several times, means additional time that I lose in the post-processing before I can analyze my data. So therefore, our developers came up with a smart idea of having some filter capabilities, some correction capability in the real-time path. So if you have here a look on this high-level block diagram of our oscilloscope, we see, of course, the signal channel here again with the channel input with the AD converter, and then within the acquisition unit, before the data go to the memory, we have some filter block that we can use for correcting some transmission loss there. So this is in real time. These filters are working in real time. And of course, they have, let's say, certain capabilities. And then if you need more correction, more accuracy for analysis, of course, also in the post-processing, we would have additional filter capabilities. So what are the steps there? Of course, both filter blocks, they are configurable. So the user, he has to provide some S parameters. And out of these S parameters, our software calculates a correction filter. And then this correction is applied. We see here on the very right side, let's say the yellow trace shows what is the transmission loss uncorrected. And the green trace shows the corrected frequency response. So the solution from ROHDE SCHWARZ is that we have some real-time filter structure that we can use for correcting transmission loss. And the individual steps there to set this up are shown in the middle here. I define my signal chain. So from the device, there might be some test fixtures included, there might be some cable included until it goes to the input of the oscilloscope. So I need to define this signal chain. And then for every component within the signal chain, I can apply S parameters. And then all these S parameters are combined, and out of this, the correction filter is calculated. And the result you can see here on the bottom picture, we have two signals. On the right side, we have a very, very short cable. So for us, it was an idle cable. And on the left side, we have a lossy cable where we applied the correction. Now you don't see a difference in the amplitude, for example, anymore, because the correction was applied to the signal. So with this approach of having filter structures in the real time, we can maintain this high acquisition rate of the ROHDE and SCHWARZ oscilloscopes. And with this, we can continuously also, with de-embedding, collect very fast the data bits. So these were the 5 steps for setting up an eye diagram. Now let's have a look to the oscilloscope that is behind all these innovative functions. It's about our RTP oscilloscope. There we have different models with bandwidth from 4 GHz up to 16 GHz. You can see the respective sampling rate of 40 gigasample. You can see the memory depth goes up to 2 gigasample as a maximum. We have 2 different options of clock data recovery, so up to 16 gigabit, supporting the 16 gigahertz oscilloscopes, and so on. And let's have also a final look to the architecture of this oscilloscope. Here again on the block diagram level. So on the left side, we have a device with, let's say, a certain characteristic of a signal quality that we can see in the eye diagram. Then we have a lossy signal path. For example, we have some traces, we have some cable. So already a distorted signal is entering the oscilloscope. Then we can recover by real-time de-embedding the signal. Then we can apply the differential math. So we can calculate the differential signal, the common mode signal. Then we can apply the clock data recovery as a hardware trigger. And then we can apply mask test and histogram, also supported by hardware, in order to get very fast and comprehensive results. So far about the theory of the eye diagram setup. And now in the next step, I would like to invite Matthias to give us a demonstration on the instrument itself. Matthias,
Thank
please.
you, Guido. So let's have a look up at the setup we have provided here. I'm able to sacrifice my USB demo stick. I have a breakout board that basically separates the transmit lines, which I have here connected to channel 3 and channel 1. I provide the USB power to the USB memory stick. And to show some effects which are important to demonstrate, I connected the internal waveform generator, the B6 option, and basically add a few small disturbance on the USB power supply. So we have added here just a small amplitude of a 10 megahertz signal. And we will see the effects later on if we try to distinguish between the serial and the differential mode acquiring data. Let's start with the serial one. As I said, I have the TX plus on channel 1, the TX minus on channel 3. And doing the analysis, I just have the channel 1. So I'm interested in eye pattern. I turned already on. I need to turn on a double edge, both edges, for the triggering. In order to evaluate the eye as Guido described, I now can basically enable the vertical histogram. Changing the histogram parameters, I can set it to horizontal now, because I'm interested in the jitter. Turn on the relative path from 0% to 100%. And make the threshold, the vertical threshold, as small as possible around the center. Now I have to set the record length accordingly, so that I have about 1.5, 1.75 UI. So I will do that here. So this one eye, I can change it a little bit and shift it. So this is a trigger point, and the trigger will basically remove the jitter, so this is not suited. I need to shift it a little bit more. So I shifted it now about 2 UIs further down. Now I see 2 histograms for each crossing one. Unfortunately, they're not the same. So we're going to measure the jitter first, means we turn on the automated measurement functions. In the measurement group 1, we have already selected the histogram. We can just enable that. We're going to measure the waveform count, the peak to peak as a difference between min and max, and the sigma of the distribution. This gives us some results. And also what we're also interested in are the vertical eye closure or eye opening. In order to see that, we go to the next measurement group and enable measurements on the eye pattern. Here I have the extinction ratio, the eye height, and the Q factor, which I will turn on. And you see, for example, the Q factor is about 7. And in order to a meaningful measurement, because you see the histograms are different, I have to change a little bit on the histogram, that I basically have just 50% to capture just 1. But the important message here was already that the histograms on each edge were different, which is sort of an inaccurate measurement. So here you see about a sigma of about 7.6 picoseconds as a variation. So this was the standard case. Now let's have a look what will change in case we basically use the differential mode. How do I enable the differential mode? I basically go to the channel menu and tell them now to use the differential mode between channel 1 and 3 in this case. And now we're going to turn it on. So what's happening here? Essentially, we see the 2 original channels have been grayed out, and we see the differential channel in yellow, color-coded here with the persistence setting, as well as the common mode available here. Now, in order to have good results, it is helpful to deskew the whole thing. I did that prior to this session. So I'm able to do that, a little bit cheat, but that also will improve, as you can see later on, the common mode. Means the peak-to-peak measurement of the common mode will basically be reduced. We have a feature here to compensate the D-skew. It's minus 18 picoseconds, which I put in. This gives a more accurate measurement. We see already the eye pattern as we did before. The trigger can be set to the difference between channel 3 and channel 1. And now we get an accurate setting, and we do essentially now the same. We will turn on the histogram. In this case, we can close the histogram 1, just reuse the histogram we had before, change the input. The settings are already appropriate, and we just need to enable that. Here we can go to 100% to check whether both look similar, both histograms that we see. And the first observation is already the histograms are not the same. We still have a certain dependency depending on the trigger position. If you're closer to the trigger, the jitter is obviously smaller. If you're further away, the jitter is larger. So let's turn on the measurement and check that. We have the same setting as before. We have the waveform count, the peak-to-peak as difference between min and max, and the sigma. We turn it on. And we see already some improvement in the sigma. Let's check the eye closure or the eye opening. We use the same measurement function before. We switch to group 2. We need to change to the differential channel. And now we can enable the same eye measurements. And we see already some improvement in the Q factor as one figure of merit, means the disturbance we introduced by the 10 megahertz on the supply is already reduced, because this is the difference between P and N, and we eliminate that. But still, the problem with the histogram, how do we address that? Basically, by using the trigger, the serial pattern trigger on the differential mode. Let's turn that on and see what the outcome is. So we go to the trigger menu, and there we select as trigger type the serial pattern trigger. It takes some time to reconfigure the machine. Once we have done that, we basically put in a reasonable nominal bit rate. In this case, as we have USB, we take something around 4.9 gigabit per second. As a bit pattern, we use XX, so don't care. We take everything here, and yeah, let's check what the outcome is. We basically don't need the shift in the position anymore. We can go back to the origin. And here we are. We see, first of all, a very nice eye pattern, which is extremely symmetrical. Have a look at the two histograms for both edges. They look identical. We have a very good Q factor for the eye. And in terms of measurement of the sigma, let's basically reduce in the histogram the covered range to 50%. So we just measure one histogram. And this also gives us an improvement in the sigma, means the jitter is reduced and more accurate compared to the single-ended measurement here. If you measure differential high-speed signals, single mode is not sufficient. You have problems with disturbances on power supplies that may introduce common mode contributions. And also you have to trigger with the serial pattern trigger in order to avoid ambiguous jitter results, histograms, depending on the data edge. So you need both the differential mode and the capability to trigger properly on the differential signal. So having said that, I would like to return to Guido.
Thank you, Matthias, for this interesting demonstration. As you knew what Matthias is presenting, I would like to show you a quick summary of the results. So maybe on a slide, it's easier to see. So in the first step, Matthias used just an edge trigger. So here you see that the edge configuration on a single-ended signal. And you can read the standard deviation of the first histogram, the peak-peak jitter of the first histogram, and also the extinction ratio and the Q factor on this eye. Very important for this first approach, it really depends on the position of the edge. So if I go to the next edge with my histogram, the values always will be different. So then as a next step, we applied the differential signal to the trigger. So you could see for this for this case here, where we have the histogram on the first edge, some improvement of the standard deviation compared to the first number, and also on the peak-peak jitter, extinction ratio, and the Q factor. But this is all related to this first edge here. And now in the third step, Matthias, he used the hardware CDR as a trigger reference. And now, very important, the histograms are independent on the edge position. So the histograms here are identical. And then we see the values there that can be achieved on every histogram. Okay, so I hope this was valuable information for you. Let's come to the summary. The traditional approach to do eye diagram measurement is based on signal acquisitions. You have a burst of the signal, you do some post-processing of the clock data recovery processing and the bit overlaying. And this, of course, means I look to a signal for a certain time, then I'm blind for a very long time, and then I look again for the signal for a certain time. With our new approach, where we use the hardware clock data recovery for the data eye analysis, we do continuously observation of the data eye. We have a very fast approach to collect a lot of data, and we use a lot of the hardware features within the oscilloscope in order to enable this high speed, like the differential math block, like the clock data recovery in hardware, like the mask and histogram as analysis tools also in hardware, and also the de-embedding in hardware. And with this, we come to this result of this ultra-fast eye diagram, where we can use all the benefits, and we can read what is the characteristic of our device, what is the jitter here in the transition. We can catch with the mask some rare interferer and so on. With this, we are at the end of our presentation. We hope you could gain some valuable information for enhancing your digital design. We say for today, thank you very much and goodbye.
Thank you and goodbye.